All right. Ready for the next topic? All right, so this is a course on data structures. So what we do is we name what kind of data we want to store and what operations you want to do on them. And if you limit the operations, then you might be able to have a really fancy little implementation that's fast. All right? And if you're Google and wanting to find the shortest path between two nodes, the algorithm you use is dynamic programming, Dijkstra's algorithm. And, oh, no, I lied to you. Well, Dijkstra's algorithm is a good algorithm, but we use this not for Dijkstra's algorithm, but for minimum spanning tree. All right, another fine algorithm we learned in 3101 is minimal spanning tree. And it uses this data structure. All right, so what are the operations? Is you have a bunch of objects and you build them into sets. All right, so this operation here is you take one object and you build the set containing just that object. All right, and the other thing you can do is you can take two sets and take their union. Right, and another thing you can do, but that deletes the old guys. Another thing you can do is I can name an object for you, and you tell me which set it's in. All right, and they're not written here, but let me tell you, if these are your only operations, then you can never have an object in more than one set. So how would that happen is you make a set with a 5 in it, and then you make a second one with a 5 in it. You can't do that. You should only have one 5. Right? That's another system invariant. Right? Everybody get this? All right. And all right, so various implementations, but let's focus on this implementation right here. All right, so what you're going to do is instead of a tree, you normally point to your children, right? But in this tree, things are going to point to their parents. So this here is one set. And if you were to say, hey, 11, right, there's pointers into each of these. So if you want to know about 11, you can go in and find 11, right? And then you might want to say, hey, 11, which set are you in? So you walk up the parents until you get to the root, right? And root, well, here the root either doesn't have a parent or has a self loop. Anyway, you identify who the root of this tree is, and then you say, 11, what set are you in? Well, I'm in the set whose root is 5, right? And if you ask, hey, 6, what set am I in? Well, you follow the pointers till you find its root. I'm in the set whose root is 2, right? Does that make sense? All right. And now, how do you do a union? Is if you have set 2 and set 5, and you want to union them together, you just have the root of the one point to the root of the other, right? And if you're a little fancy, you could say, well, which one's taller, and have the short one point at the big one, right? Everybody get how we're doing unions there? Now, I told you how to do a find already, right? And is you walk up the tree to find the root, right? And how much work is it to do that? How many of your primitive operations? Well, it's the height of the tree, right? So we want the tree to be short, right? And when we were doing AVL trees, right, we had it balanced, and we want the height of the tree to be kind of log n, right? But here we're going for big. We want the height of the tree to be more or less 5 or smaller, a constant, right? Now I put 5 in quotation marks. We're going to get there later what I mean by that. But let's just say for all practical purposes, we want the height of this tree never to be bigger than 5, all right? So that the work going up is a constant, right? Is this 5 in quotation marks, all right? Right, so this is saying you can do it in log n time if the height's log n, but I'm wanting the height to be 5. All right, so now, what do we get? Here, let me tell you a joy of big O. If I do something and it takes me this much time, right? And for some reason I decide I want to do it again, does it change the big O if I only do it twice? Right? It just doubles my time. Us theory people, we don't care about doubling time. If you did it once, do it twice. All right? So what we're going to do is when we look, here's our tree, and we're looking for the 3. We find the 3. We walk up from 3, and we find 5, right? And now we know 5's the root. And we just had 1 pointer going up. These batteries are giving me sound. So let's just finish this, all right? So remember on the example of blow up balloons, and then I pop, when they're popped, I throw them away, right? And that you can't pop a balloon more than once, right? So this is the same. I could build this big structure where 3 is really deep. But if I ever look for 3, and I look for 3, it's going to cost me a lot. But if I look for 3 again, it'll be cheap, right? And this is saying that on average, the height will be what we call log star. But I claim that it's even better. It's inverse Ackermann's function, which we don't want to bother you about. Just trust that inverse Ackermann's function is 5 or smaller for all practical purposes. And let's call that done. And you want code? Here's some code.